Okay. Since there is no camera today, I can skip appearing in the front of the camera. So last time we did agree that we are exploring the wavy nature of electron, and before we get to electron, we need to get to an equation that generates any wave. So we did a little questionnaire, and you guys, everyone who was here wrote something that it is something wavy, like sinusoidal, then we described a wave that can be traveling, and then we superimposed the waves going forwards and backwards, and by adding them together, we got standing waves. And then we did a mathematical experiment by taking second derivative over space and time, and identified that this second derivative of a wave equal to each other with a proportionality coefficient equal to the velocity squared, right? And then I was showing a couple of movies that maybe consider as fun, maybe not. Here we did this ancient TV. Here is the interference pattern. If source is a wave, then on the screen there will be stuff that goes with constructive and destructive interference with and without signal. And if electrons in the vacuum tube give this pattern even in the macroscopic vacuum tube, how strongly they should interfere in the atom and molecule. So it is unavoidable to consider the wavy nature. So couple of movies here that I can play them again, but they illustrate the concept from which quantum science did start. In order to explain special form of the observed atomic spectra, there was a Bohr model you've heard of, where one assumes that electron is moving on a linear, on a circular trajectory around nuclei, but exhibits wavy nature. It is an obsolete theory that we are not going to use for describing of any modern science effects, but it is important pedagogical thing that simplest step from classical consideration when both electrons and nuclei are point charges to the quantum nature. And this is quite simple model so that one can process it without any special preparation. So at the end of the class, I hope we will go in more details, and some of you may select this model for projects because there are some interesting observations. So what we are looking here is this green line, which is like amplitude of probability of electron being here and there, but 0 point is on this black circle. So if it goes away, it is this notation works. So when it goes away from the center, when it goes away from the center, it is positive. When it goes in towards the center, it is negative. Very good draw. And on the next one, we have two instances when it is positive, three instances when it is positive, and three where it is negative, which means it is like a standing wave that goes on the surface. It is not quite productive to focus on it. We take it only as illustration, but to have your education solid enough for the future, we will return to this model maybe in 3 months. Cool. And here
Never gonna give you up, never gonna let you down, never gonna run around.
Observe for the future. So the wave is which wave moves quicker, with larger number of fringes or smaller number of fringes? So later on we will see consequences, same trends in other objects. And here is a little another movie where one is trying to set up standing wave with even or with integer number of this lobes and nodes, and then if one artificially makes it not non-even. If it is integer, like here, there, it looks, you will see that keeps its shape, so it moves radially but doesn't change the shape. And if one selects this non-integer numbers, something non-beautiful happens on the right panel. And the following statement is not rigorous, but it is but true. Any theory that is beautiful is correct. Anything is ugly is wrong. So those ugly images on the right correspond to states that either do not exist or exist for so short time that no one can observe them. And one of the observations made in an experiment, and then theoretical background developed by the theory that the electrons in the nuclei can move only with certain characteristics, certain speeds, certain angular velocity, certain energy, not arbitrary. So if it is non-specific, if it is not one of these magic numbers for these observables, then it doesn't exist and doesn't give contribution to experiment. So it was the first step of the theory. And if one wants to be a little bit more detailed and rigorous, then the thing that needs to take discrete values is so-called angular momentum. Let me know if you have heard about how comfortable and familiar you are with the concept of angular momentum. Right? So measure of angular motion, like velocity of momentum, linear motion is measure of linear motion, angular momentum is measure of rotational motion. And if it is a single, like, just a second. Oh.
Such a strange class. This is crazy. You found, I think it's started one time after. And then some class we have started one time after. Wow. Have you been anything yet? What's that? Have you learned anything yet? All that.
So observation, well, we are skipping details of this theory, but if one goes through all details, the main statement is that absolute value of this angular momentum takes only discrete values. And then let's go through a few more details. So I think it will be really cool if you try to write down and then answer to me, what is your vision, what is your definition of angular momentum. It doesn't need to be equation, you can just write down your impression of the concept of angular momentum. please try with the more the discussion. And Spencer, Adam, and August, you may try to write it on your notebooks as well. So what do you have?
Angular momentum, the momentum a particle has at t time in its path.
Please repeat.
The momentum that a particle has at t time in its path. The relation to time, momentum relation to time.
Probably it's a new word in the science. It is. Well, later we will do something related to the past, but I would say it is an observable that is bigger when object rotates quicker.
I just said a particle that's moving with respect to a point where the angle is changing.
Okay. So yes, but in your definition, there is if it moves slow or quick, it will be the same. And angular momentum is measure how quickly angle is changing, right?
Yep.
And let me attract your attention to this little ugly drawing. So if we have an origin here, and we have a particle moving with momentum p, and as time and radius r from the origin. As time goes by, it accumulates this angle, right? And the quicker angle is changing, the bigger is angular momentum. In like vector calculus and physics classes, one defines radius as vector, momentum as vector, right? And then angular momentum is vector perpendicular to the plane of the rotation. So it is cross product. Of radius vector and angular regular momentum. And the units of this angular momentum we will consider it in the next couple of slides, but there is a fundamental constant designed before this Bohr model, Planck constant, which has the same dimensions as momentum. And if one looks on the value of angular momentum in terms of Planck constant, then it will be in units of either radians angle, or if one divided by 2 pi, it will be just dimensionless. And the statement that comes out of this Bohr theory that permitted states of electron in the atom are only those when angular momentum of the rotation takes integer numbers. So it is not the whole quantum theory, it's only an first step. And we are going to do several problems, several natural objects, and we are going to come to similar conclusions, not in a philosophical discussion-wise, hand-wavy stuff, but by derivations. So it's just a little heads up. And in order, let me share the goals. First, about 5 lectures are, I wouldn't say they're boring, but they are non-usual. It will be a lot of ideas rather than mathematical derivation and standard learning. And they're quite complicated to communicate. If one formally defines these ideas, it will be so boring that you will come to an idea to drop the class. But if you discuss it freely in different funny way, then you'll find that these ideas are beautiful, and then you can come to mathematical implementations. So I do not know how to explain it, but if we accept that electrons, if we temporarily accept that Bohr theory is not so bad, and that electrons exist only with fixed value of angular momentum, what is discrete? What is changing when we are going along this circular path? And in general, why this angular momentum stuff related to angular momentum should take discrete values? Can we do any connection to wave equation? Can we bring any quantitative explanation, like if you do not know Bohr theory, how can we imagine that it is correct? What are the reasons for this very strange conclusion? Because in regular life, if I have a stone and a rope, I can make it revolving with any arbitrary angular momentum. The wheels on our car, depending on if I push pedal to the metal or not, it takes continuously. This strange condition, it looks like speed limits on the road, not like forbidden above 90 mph, but you are allowed to drive on with 10 mph, 20 mph, 30 mph, and if you do ±1, you get ticket. So it's quite strange. It's not natural for our regular world. We do see that somehow it is related to this interference and fringes, and maybe this integer number is related to number of this humps, but it is quite hand-wavy. You need to bring more solid language, more ideas backgrounded on something solid, and I'm going to try it. So it is not like standard set of definitions that I just mumble, you memorize, and we're okay. It's an idea that can be hidden between the lines of the sentences. So I'm inviting you to follow ideas rather than words. So if we want to go to a quantitative description of the stuff, we may make a step back and look on the classical particle moving on a circular trajectory, and try to remember or derive how one can predict the trajectory, where these trajectories are coming from. So with this question, how to predict trajectories of solid point masses, material objects in a regular life, we are coming to physics, either in high school or if you are taking the college physics. So mechanics. Which equation predicts trajectory of a mass? This word is written there, but you need to point the right one. And Spencer, Adam, and August, if you like, you can also try to type the answer. So, which equation predicts trajectory of material object in classical physics? It is not graded. It's only to support the discussion. So please do not hesitate to speak or type. and or better just write down.
I don't have anything yet.
Huh?
I don't have anything yet, still thinking.
How did your, do you have anything?
Not yet, no.
So what were you doing? Oh, okay. Let's see if we have. No, no one is typing. What were you doing in high school physics and were you taking college physics at any level?
Yeah.
Okay, where it starts from? What are the first subjects?
Kinematic equations.
Huh?
Kinematic
Okay,
equations.
next.
Parabolas.
Okay, next.
Circular motion.
So for parabola, okay, maybe next.
Electrostatics.
Oh no, okay, for parabolas, which equations, or which family names did appear when you were talking about parabolas? Parabolas probably when you were throwing stone in the sky, right?
Yeah.
So why it returns back and why it returns back quicker and quicker and quicker? Who is responsible for that?
Newton.
Yes, Newton wrote what?
His three fields.
Laws, and which law is circled here? Like action is equal to counteraction.
Positive and opposite reaction.
What else? I would say it's second law. So why stone that you throw in the sky falls down quicker and quicker? Why it accelerates?
Gravity.
Yes, gravity force. So force creates acceleration, right?
Yes.
So, okay, then we have just a little lost semantics, but you know the concept.
Yes.
So the reason for acceleration is force. Force creates acceleration. This is Newton's law, and there is a Newton's equation, which is F equals ma, or acceleration A equals force divided by mass, right?
Yes.
Now, what is acceleration?
Instantaneous movement.
Huh?
Instantaneous movement.
Okay. How does acceleration connect with velocity?
V equals ma.
Only for a circle. More general. Like, okay, let's start from very basics, and it's fine. We have time, and later on we will go through material like rocket, but solid basics make the life easier. So, what is velocity?
Speed.
What is speed?
Movement.
No, mathematically.
Distance over time.
Yes, this is absolutely correct, and you may even write it down. And one may add a little bit. Okay, obviously, typing Newton's law, change of velocity versus time, the derivative of velocity, right?
Yes.
So it is the same with a little bit more details. So not just distance over time, but increment of distance over increment over time. So that if it moves quicker and slower, it will still work. The definition will work. Now, one can escalate this style of thinking, and instead of distance over time, make a derivative of velocity over time. So derivative of velocity over time will be acceleration. So how quickly velocity is changing, right? Or second derivative of position over time. If you do not quite remember, you may write it down. Acceleration is second derivative of position over time. If you're comfortable with this. So this is a basic knowledge in this circle, so that in order to predict trajectory of material object, one practice second law of Newton or Newton's equation, and practices d2x 4 dt squared equals force divided by mass. So if you know the force and you solve this differential equation, you can predict position over time, predict trajectory. And the goal of mechanics is predict trajectories. In chemistry, in quantum theory, we will be more ambitious. And things are more complicated. And my goal today is to bring us two equations for electron in atoms and nuclei. And there are several concepts. If we start immediately with the equation, it will be very boring, at least even for me. So now we will squeeze the advanced physics at the graduate level in 10 minutes. So this is well accepted, Newton's equation to predict trajectories, but there is another way, another scientist who gave competing theory that answered the same question. So it is a Lagrange. He was acting at the time of Napoleonic Wars, a little later than Newton, and his theory is not as simple and self-concise to teach it at high school, but it is a little bit more universal and works for more complicated systems. But in essence, it is same second Newton's law, but it is formulated in different. You'll see it in the next slide. And based on the Lagrange theory, we can feel the connection to motion of electrons. We can define such concepts that will help us to live happily. So I'm closing chat for a time. So I'm going to read you a couple of concepts that were present in Newtonian formulation mechanics. They're also present in Lagrange formulation in mechanics, and we will borrow them from mechanics to quantum theory. So one of the concepts is trajectory, which is just position over time, right? You can write x of t. Another is kinetic energy, which is either mv squared over 2 or what? 1/2 mv squared. 1/2 mv squared, yes. Or one can do 1/2 masses momentum squared, right? If momentum is mass times velocity, it is equivalent. Potential energy, it is different anytime. We can use just the letter V for it. For harmonic potential, it can be just x squared, but let's be not specific. Then sometimes people use letter U. The Hamiltonian is operator of total energy, and it is typically formulated as kinetic energy, and often uses letter T because I don't know why. T plus U. So total energy, kinetic plus potential, is total energy of a moving object. And probably Lagrange was jealous to Newton, and he decided to do something different than Newton. I'm joking. And he decided, why don't I subtract kinetic minus potential and tell that this difference of kinetic and potential is more important than their summation. And I do not know interpretation. It's just very comfortable mathematical concept. If one, instead of total energy, works with the subtraction, it gives some benefits. And then there are equation of motion. So for Newton, it was second derivative of trajectory equals force divided by mass. And for the Lagrange. It is let me check on that. Yes. So one can set up the combination of differential operators acting on this Lagrange, which is like inverse total energy, or how to say, subtraction of kinetic and potential. And by solving this equation instead of Newton's equation, one can predict trajectory, find how position changes over time. And there is a very, very interesting, important, and mind-throwing concept out of this formulation. So if one goes from the initial point of time, initial point of trajectory, let's just from initial to final, and then takes Lagrangian over of the along the trajectory, then this value is referred to as action. And the more motions system makes, the higher the value of this action. And this action depends on initial time and final time, initial point of trajectory, final point of trajectory. So if we look for short interval, action will be small. If you look for as long as we go through motion along the trajectory, action will grow, 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 grow. If it will, if something moves quickly, it will grow quicker. So, do you have any conceptual objections against this definition, especially the last one, or is it quite normal? Okay, so we just subtract kinetic minus potential energy and integrate it along trajectory. And there is a, you do not need to memorize all the things, but you can just get general ideas. When we will come to solid stuff that you need to memorize, I'll give a sign. So there is I apologize for giving too many theories, but there is a third, well, wait a second, but there is a following statement. Instead of solving Newton's equation or Lagrange equation, one can take a kid from kindergarten, give him a pen, and let to draw arbitrary trajectory. Then call for advanced scientists and request to compute action along this trajectory. Then using another random number generator or another key, draw another trajectory. Compute action along this trajectory, starting from the same initial and final point. And then compare thousands of different trajectories. So the trajectory which gives the minimum action will be demonstrated when we do experiment. So like nature is lazy. Nature starts to practice, tries to practice those trajectories that minimize action. And in our principle, least action principle, that among humans we call laziness. So it's fundamental. Here are the same equations, just if you do not like my beautiful calligraphy. So today's recording will be without video. I don't know if it is a plus or minus. And now we need to touch the dimensions in the Bohr's model and try to bring these concepts together. So what are the dimensions of this angular momentum? And when we do dimensions, we can forget about vector nature. Let's just look. So distance, just measured units of distance, like meters or inches or whatever. Parsecs, if we are speaking about astronomy. Momentum is mass times velocity. Velocity is distance over time. So overall, the dimension of the angular momentum. So if you take this x power 2, distance squared times mass divided by it seems like I could, shouldn't be squared. Okay. I was trying to be too quick. So now I can multiply it and divide it by time. Do you follow it? So if I multiply divided by time, it will be x squared divided by t squared times mass multiplied by time. And x squared over t squared times mass will be like mv squared, right? Which will be kinetic energy. So energy times time. And it is a very interesting observation that the units of angular momentum, which is like how quickly the angle is accumulated, how quickly rotating object is rotating. Right? So the units are the same as energy times time. So I'm going to draw a little crazy conclusion, make a bridge without sufficient fundamental, but I'm just inviting you to try this imaginary game, and later on we will make it more solid. So on one hand, we have Lagrangian theory and least action principle, which tells that action, which is energy, Lagrangian energy times time, must be minimal, right? On another hand, we have a fact that dimension of the angular momentum is energy times time. So action in Lagrangian principle and angular momentum in our Bohr model or any rotation have the same dimension. Now we are going we unleash our imagination and tell, why cannot we describe circular motion with least action principle? Why can we say that only those revolving trajectories which give minimal action will be correct? Or maybe a little bit modified, since we are going to microscopic work, only specific trajectories that impose specific conditions on the action along the trajectory. Not minimal, but some specific. Please try to record it, write it down in your own words. I do not know how to tell it better. So only those trajectories that have some specific conditions imposed on the action will be allowed to exist in nature. if you do not know how to formulate it, just conditions on action. So we are still in this quite uncertain area, but if we try to summarize the things that we were discussing, we can formulate it this way. When an electron is revolving around the nuclei, it accumulates action, right? And while it accumulates action, something is oscillating. These oscillations are more vivid, it oscillates up and down more quickly as the bigger the action. So accumulation of action results in oscillating of waves of some nature that define allowed states of electron in the nuclei. And this is an idea that we need to process further. So we need to discuss, we need to speak on the language of action being accumulated along the path, and we need to find how this accumulation of action results in fringes of something. We didn't define what is oscillating, and then impose conditions. Which values of action, which states are allowed. Make sense? Okay. Yes, I was expecting that it is the last one. And we are done almost in time. So meeting is done. You're welcome to depart. If you have some questions, I'll stay here.